British weather. Traditionally the most unpredictable aspect of our daily lives. But how unpredictable is the weather? Today in this lecture we're going to look at hidden patterns in things that seem to be irregular and unpredictable. Isaac Newton's great breakthrough was the realization that the universe runs on mathematical rules. It's like a giant clockwork machine. And that point of view led to what's called determinism. This is the idea that everything is laid down from the very beginning. Once the universe is set up and starts running, it's going to follow exactly the same course. If you ran it again, starting in the same way, it would do exactly the same thing. It's as if the whole universe is predictable. And that idea led Pierre-Simon de Laplace, very famous 18th century mathematician, to an astonishing vision of a super intelligent being which could predict the whole future of the universe using a single mathematical formula. But is it really like that? In earlier lectures we looked at patterns in the universe. In this one I want to look at the opposite, disorder, irregularities. It's called chaos. It's a relatively new area of mathematics, and we'll see it has a lot to tell us about the world we live in. Now with chaos, it's all around us. We tend not to notice it. This flag flaps in the breeze. We're all used to flags flapping. What we never notice, the breeze here is completely steady, it's just a fan, and yet that flag is flapping irregularly. Where does the irregularity come from? Here we have a candle. If I blow out the candle, the stream of smoke coming off starts regularly and breaks up into all sorts of complicated vortices. Where does that complication come from? Candles always look a bit like that when you blow them out, but they're always complicated. This lava lamp, you've all seen these. They make patterns, they move quite slowly. The pattern is never quite the same twice running. Yet all we've got here is some wax in water, and underneath it's heated, gently, uniformly heated. Yet it makes all these patterns. Again, why is it doing that? And here we have, specially made for us, there's a man called Alan Bennett who blows glass, and he's blown us some chaotic glassware. And what's going to make it chaotic is this little bulb up here. The water's building up in there, and in a moment this will start to do some quite surprising things. You'd think it's just glass tubes, the water flows through. What else could happen? Here we go. Whole series of bubbles coming through. And although every time we run this you get these bubbles coming through, you can't predict just how many and exactly what the timing is going to be. It's another example of chaos. I want to look more closely at chaos, and we're going to try and find out what it is about it that distinguishes it from regular behaviour and how it works. Now to do that, to start us on that, we're going to need a volunteer from the audience to come down. Young lady there, come down. Come around here. Okay, your name is?
Caroline.
Caroline. Okay, Caroline, what we've got for you is an egg beater. Come up here. And I've got the eggs here, and I'll break them into the bowl. And when I've done that, Gary Rhodes, eat your heart out. I want you to whisk them up. That's it, give them a good beat. That's great. Okay, now stop there, we've got a bit more to come, so put this horribly messy thing down here. Okay, now we've all seen that, and there's a question about egg whisks that we hardly ever ask ourselves. You probably never thought of this until I raise it now. How do they work? How come when the whisk just goes round and round, the egg goes all over the place and gets mixed up? The egg beater doesn't get mixed up. Well, we've got a giant egg beater around the front. You want to come around the front? We're going to show you how it works. Now let's just take a look at what we've got here. It's a big egg beater, and in it are 3 lots of ping pong balls. White ones, purple ones, pink ones. And we're going to see what happens when all you do, turn the handle gently. There are these pins inside, and we all know what's going to happen. Let's see if it does. Okay, you want to grab the handle there, give it a really good turn, keep going. Okay, that'll do, I think. Fantastic. Okay, thank you very much. Applause. Now, let's just think about how that worked. The arm goes round and round, the pins go round inside, and something in there starts to mix up the ping pong balls. Now, what must happen is that ping pong balls that start close together end up far apart. Otherwise, all the pink ones would stay together. They don't. They get spread all over this device. So what's causing the chaos here is the way the pins are moving the balls apart. They're pulling things apart, they're mixing them up. And that's where chaos comes from. This tap's been dripping over here for quite a long time. One of the signs that a system is chaotic and not random is if it starts out looking regular and you make very small changes and it becomes irregular. If you've not put any randomness in, it can't be random, it must be chaotic. Now this is a regular deterministic tap, sort of tap Laplace would have loved. Drip, 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 we can hear it. Now I'm going to just turn the water on a little bit more, and we'll see what happens. There we go. Okay, now it's trickling in an irregular fashion. All I did was turn it on a bit more, and yet now the flow seems random. But it can't be. It's governed by the same rules as the regular flow. Okay, so what we saw there were several different chaotic systems. They're all little gadgets, little machines, sort of things you find in your house, sort of things we can build here. But I want to talk now about 2 very similar real-world systems, one of them regular, one of them chaotic. The regular one is tides, the irregular, chaotic one is the weather. Tides first. Tides happen in the sea, they happen in the oceans, and what happens there is the oceans fall and rise. It's fallen. You all know if you wait long enough, the tide comes in, scares away the bird, and rises. Now that's a very, very regular thing. It's so regular that you can get an almanac, 1998 almanac, and inside are the tide tables for the whole year. They tell you exactly what time it'll be high tide, when it'll be low tide. And that's because the tides are predictable. You don't find books of next year's weather. Why are tides predictable? Basically, they are caused by the gravitational attraction of the moon. The Earth revolves, the moon seems to go round the Earth, and the oceans pile up underneath the moon. The sun also pulls at the oceans. It's a combination of the two. To keep it simple, I'll just talk about the moon. And we're going to do a demo in a moment where all of you are going to be the ocean, and the moon will be a spotlight. And the spotlight will come round, and as the moon comes round, so as the Earth rotates and the moon is overhead, I want you to just put your arms in the air like this, put them down again. Okay, so the moon's on its way. Let's see what happens. See it? Fantastic. And we'll do that just once more. As the moon goes overhead, now the motion of the moon is very regular, very predictable, and so that's why tides are so predictable. Weather is very different. Just look at the weather. Clouds look complicated, the motion seems more complicated, and yet tides and weather really mathematically are very similar systems. Tides are caused by the gravitational pull of the moon and the sun acting on the oceans, and weather is caused mostly by the heat from the sun acting on the atmosphere. And the mathematics of oceans and the mathematics of atmosphere is very similar. And yet, there's a big difference. Tides are the sort of thing you'd expect in a clockwork universe. Weather is the sort of thing you wouldn't expect in a clockwork universe. Now, I'm going to show you that even simpler things, things that obviously are clockwork, work like the weather. They're also unpredictable. The simplest piece of clockwork is over there. It's part of a clock. It's the pendulum. It goes to and fro regularly, repeatably, predictably. Now, you might think that if you took two pendulums and stuck them together, then because each one is predictable, surely when you stick them together, the result is, again, predictable. Well, let's see if it's like that. Okay, so here we have a machine. It has two pendulums on it. The lower pendulum, and there's another pendulum at the top. And I can just set the whole thing going like that, and it seems perfectly regular. But now we'll see whether it always does that. Now I need a volunteer to help me do this. Okay? Up you come. What's your name?
Anthony.
Okay, Anthony. Now, what you're going to do, stand just a little bit, that's it. I'm going to get you to grab that about there and give it quite a good hard push. That's it, and let's see what it does. Here we go. And now it's suddenly swinging round and round, sometimes one way, sometimes the other. And it's very hard to predict what that's going to do. There is a mathematical rule behind it, but you can watch this for quite a while and not really be able to anticipate exactly where it's going next. Okay, it's settling down now. Yeah, I think we'll stop it. See? I'm just going to stop it and it's off again. It's amazing. Right, I think we'll stop it now. Okay, now I've got another demonstration here to show you just these things really are following rules. This is, and Anthony's going to help me with this one as well. Here we have a cylinder. It's full of gel. It's got a red line down the front. It's got a blue line down the back. That's ink inside the gel. There's a handle on top. What I want you to do is just turn that handle slowly 3 times and we'll see where it all goes. So 1, 2, 3, stop. Great, that'll do. So now look what's happened to all that gel. It's all got mixed up, smeared, streaked, okay? But I'm going to show you that that's not randomly mixed. We're going to unwind it, put it back where it came from. Anthony's going to unwind it. Okay, so back 3 times. 1, 2, and 3. Stop there. Look at that. That's not bad, is it? Okay, Anthony. Thank you. So I know what you're all thinking. How about unwhisking the egg or unmixing those ping pong balls? Well, if we could exactly reverse the motions, that would work. It's a deterministic universe. It would simply undo what it did before. But there's a practical problem. It's not just the position that counts. In those, it's the speed. In the example we've just shown where we did manage to undo the whisking, only the position mattered, and that was easy to reverse. when the speeds come into it, it's almost impossible to get it working right. But what is it about rules that leads to such complicated behaviour? I'm going to show you that simple rules really can produce results that look almost completely random. And I'm going to need a volunteer for this. And young lady there, that's it. Okay, thanks, Ilya. Thanks, Bipin. Okay, now, you stand here. This is called Langton's ant, after Chris Langton, who invented it. And the ant lives on a grid of squares, and those squares can either be white or black. And we've put up some rules for the ant. Okay, and we're going to take you through the rules, and you're going to show us what happens. So the first ant rule is the ant moves one pace forwards. If it did that, it would be on this square. The next rule is if that square's white, turn right. If it's black, turn left. And then after you've done that, go back to the square you've just left and change the colour. Okay, now what's your name?
Rachel.
Okay, Rachel. Take us through the first step of what the ant does. Here he goes. He takes one step forward. I'll do the commentary. It's white, so he turns right. Right on white. And we change the square he left. Do it again. Where's he go next? Goes forward. He turns right again. And that square goes black. And again. Forward. Right again. That square goes black. Okay, keep going. Forward. Now he goes left. That's it. Don't want to go. And that square changes. He's going off some different direction now. He goes off to that square. That's it. Turns right. Super. And the square he was on goes white again. And there. Turns right. That's it. And that square goes black. Goes to here, turns right, he's heading back down that way. And this square goes black. Let's take him back to his starting square. He goes there, turns right, and this square goes black. That's great. Thank you, Rachel. Super. Well, it's not clear what sort of pattern this ant will make. The first few steps following those rules has created this nice little symmetrical pattern. But I want to find out what happens if you follow those rules for thousands and thousands of steps. Does it stay that simple? And to do that, we've got the computer here. I'll just set it up. And we will start the ant running, and we'll see what he does. Here he goes. Let me just adjust for position. That's better. So the ant is buzzing away, and he's making... These are lots of little black and white squares. Well, blue and white squares, actually. And he's making an apparently irregular pattern. He's following these rules, fixed rules. And yet, nothing very regular about what it's doing at all. It just seems to be buzzing around. You think, oh, OK, that's what those rules do. They just make random patterns. There's really nothing else to it. But it can't be random. We know what the rules are. If two different computers did this, they would do the same thing. We're up to 7,500 steps now, and it's still buzzing around at random. But fairly soon the ant is going to show us something that reminds us there really are patterns and rules there after all. Here he goes, getting close. Yep. Here we go. It's building a highway. It takes 104 steps to complete the cycle that builds that highway. And it will now go on forever. So it starts out looking jumbled, and suddenly it looks like a pattern. So you wonder what's going on there? What's happening? The first 10,000 steps, the ant is reminding us that simple rules can give very random looking behaviour. We look at that and we say, there's no pattern there. Not true. If we look very closely, we would know that there were the ant rules governing that behaviour. And when we see the highway, we think, oh, now there's a pattern. The ant's just following the same rules. So what looks like a pattern to us is produced by rules, and what doesn't look like a pattern to us is produced by the same rules. So it's our perceptions that are causing the trouble. It's not that there isn't a pattern, it's that we don't see it. So that's what happens with chaos. Now, another feature of chaos is something that the ant is a little misleading about. If I ran the ant twice on two different computers following the same rules, starting from the same positions, we'd see exactly the same things. And the reason is because it's just black and white, there isn't any room for error. But in the real world, there's always room for error. And the next demonstration here will show that. This is another pendulum, but this one's magnetic, and there are little magnets underneath. And if I start this off, it will wander around, and the magnets will push and pull, and it jiggles around, and it starts doing quite complicated, not very predictable things. It's obeying its rules. It's completely deterministic, but it's not predictable. It's not predictable because if I did the same thing again, or the best I could get, the closest I could get to doing again, pushed it in the same direction at the same speed, very quickly you'd find it's doing completely different things. Tiny errors in the direction and speed with which I started it off will grow, and eventually they grow so big that it just completely changes what happens. Now, to convince you of that, we've got a demonstration here where we'll run the same system twice side by side. Now, I need two helpers from the audience to help me demonstrate this. Okay, young lady in green there, and next to her. Down you come. Okay. Hello, and you are?
Sophie.
Sophie and Mark. Sophie and Mark. Okay. What I want you to do, what have we got here? Two beakers with water. They're being stirred by these devices at the bottom. They're as close to identical as we can make them. And you've each got an eyedropper with some ink in. I want you to pick up your eyedropper. And then when I give the word, I'll say 3, 2, 1, go. Let's take it out of there. That's it. When I say 3, 2, 1, go, I want you both to drop ink in about sort of middle of the back there. And we'll see whether they do the same thing or not. So 3, 2, 1, go. Okay. Well, they started out very similar, but very quickly they got enormously different. Okay, Sophie and Mark, thank you very much. Thank you. Okay, what we saw there, the motion started out very similar, but very quickly, so quickly you can hardly follow, the ink was moving in completely different directions, making different shapes. Now it's all got stirred up and you can't tell the difference again. It's that effect that produces chaos. The real difference between a regular system and a chaotic system is in the regular ones, tiny errors, tiny differences don't grow very fast, if at all. In a chaotic system, tiny differences grow very fast indeed. Tides are predictable because of that effect. The tiny differences in the tides don't much alter the way the moon moves, so the tides still go up and down. Weather is very different. The atmosphere can move in extremely different directions under very slight changes. So here are some clouds. They're complicated, irregular looking structures, quite hard to calculate anyway. And there's a mathematical joke about the sensitivity of the weather. If a butterfly flaps its wings, then the weather will change completely. The tiny little vortex shed by that butterfly will grow and grow and grow, and one day there'll be a hurricane on the other side of the world from where it would have happened if the butterfly hadn't flapped its wings. Okay, that's the joke. Now, the question is it really like that? Well, we did an experiment. On the 15th of December, 10 days before Christmas, we asked the European Medium Range Weather Forecasting Centre in Reading to prepare us a 10-day forecast of the weather all the way up to Christmas Day. And that's one of the charts here. We also got them to flap the butterfly's wing, to change the observations at the beginning very slightly and do the forecast again and see what difference it made. Now, to help me understand what's going on here, I don't know much about weather, so we've invited Suzanne Charlton along to tell us all about it. Okay, so what have we got here?
Well, as you say, we've got two goes, if you like, starting off from just very slightly different initial conditions. So to the human eye, you can't really see the difference at the beginning.
Right.
Then what happens is that maths and physics comes into it, and the computer works out the forecast for the next day and the next day, and so on and so on and so on, till we get to the last day, which is, of course, Christmas Day, by which time chaos has kicked in, as you might say, because you've got a high pressure, probably quite fine and sunny. I've got a low, and it looks like it'll rain with me.
Right. OK, now to make that clearer, we've animated all of those charts. And so, Suzanne, you're going to take us through the animation and tell us what's going on in more detail.
That's right. We can actually have a look at those two pictures together, side by side, prediction 1 and prediction 2 as well. Now, at first, when the forecast starts moving on through time, there won't be a great deal of difference. We'll be able to see that there's a subtle change in the pattern, but high pressure remains mostly over to the north and east, and there's something of a low pressure developing out towards the southwest of Britain. It's after this point those two different forecasts start to diverge and go off in different directions altogether. And one ends up with a high pressure and the fine weather, and the other one ends up with the low pressure area. Now, actually, they do 51 forecasts anyway each time. And I have to say, although these were the two extremes, the majority of the forecasts went for low pressure, so disturbed weather. OK, so that makes it seem perhaps as if the main thing that chaos does for us there is tell us it's rather difficult to forecast the weather, and that, in a sense, it's just saying there are lots of limitations and we can't overcome them. Now, is that really true? Well, it does that, but it helps us as well, because, as I say, there are 51 maps, so though it gives us the spread of the different types of weather that we might maybe expect, it also clumps together in some cases with quite a number of forecasts going maybe for a low pressure area, as in this case it gives us a confidence in the forecast, a reliability factor, if you like. And as I say, the 51, we can actually have a look at them all together on what's known as that spaghetti chart, and you'll see why it's called that in a minute. It's one red line, it's actually those 51 close together. This one's temperature, basically. So to the right, over Eastern Europe, it's colder. The mild weather is on the left-hand side here. And then as we run on through time, we'll start to see that the spaghetti unravels in some places as those forecasts begin to move apart. But it does show us where the forecasts are the same as well. So it's definitely no spaghetti really over Britain. We're well on the mild side of the weather and set to stay that way. So we were confident it was going to be mild. We weren't expecting to have a white Christmas.
OK, now what actually happened on Christmas Day?
Well, do you remember Christmas Eve, that storm that blew in across northern parts of Britain, one after another? And this is what our weather map at work looked like on Christmas Day, in fact, with two low pressure areas, a deep one, which one or two of the forecasts of the 51 had gone for. Low pressure, that was the main thing anyway. The longer range forecast from Reading had actually given us a hint a few days before that a clump of the forecasts were heading towards something pretty nasty, as was the Met Office's forecast too. So that gave us reliability and confidence a few days before to say something could be happening, it could be getting really windy.
Thank you, Suzanne.
That's all right.
OK, so what we saw there was how chaos not only tells you how difficult it is to predict things, but it can also make you think of new ways of predicting things and find out what's predictable, what's not, and how predictable it is. Well, it's always nice to know your limitations, but it really would be nice if chaos could do more for us than that, if it could make a difference to our lives. So the next thing I'm going to show you is where chaos has improved technology. The technology I'm going to talk about is springs. Here's a rather big spring, but springs are important in everything. If you take a video recorder to bits, you find about 500 springs inside it. Somebody has to make all those. They're nearly all different. Bed springs, car valve springs. Springs are everywhere. Now, springs are made from wire, and what makes it difficult to make springs is when the quality of the wire varies along its length. Now, that's not just a problem for the spring industry. It's also a problem for people who make things like suspension bridges. So, suspension bridges hang from enormous cables. Those cables are made from wire. The whole bridge is hanging from lots and lots of bits of wire woven together. What I've got here is a sample from that sort of cable. If we look closely at that sample, you'll see lots and lots of wires all packed together. The wires are quite thick here, but they're packed together very tightly to form the cable. And they're woven together, they're spun in a spiral, a bit like rope. So being able to test whether wire is good is important for a whole lot of industries. This particular project started in the spring making industry, and their problem was the way they make springs involves passing wire through what's called a coiling machine. And it just whizzes through the machine, it forms coils, they get snipped off at up to speeds of 18 springs a second coming off the machine. Now those springs may or may not be the correct length. And just occasionally, wire that looks perfectly good, it's passed all the quality control tests, it looks exactly the same as all the other wire, won't coil into springs. It has what's technically known as poor coilability. How can you tell the difference? Well, the way they used to tell the difference until very recently was you spend 12 hours desperately trying to make springs with your bit of wire, and you find it won't do it. And after you try for 12 hours, you're really convinced it won't do it, and so you give up. Now that ties up a very expensive coiling machine and a trained operator for 12 hours. So the new method, based on chaos theory, is a machine called FracMat. FracMat was invented by the Institute of Spring Technology in Sheffield and it's funded by the government. And what it does is it forces a wire sample to form a long coil by coiling it on a metal rod. This one is one of the samples off the FracMat machine, and this comes from good wire. And we can see it's good if we compare it with the other sample I've got here, also off the same machine with wire that looked exactly the same, but this one is from wire with poor coilability. Come on. That's it. And you can tell the difference. Anyone can tell the difference. This one, all of those separate coils are regularly spaced. So there's no great variation in the properties of the wire. This one, the poor one, they're very irregularly spaced. You see clumps, you see bits where they're too wide, bits where they're too narrow. That causes problems for the coiling machine. Now it turns out that you can take the variability here and kind of pull it apart mathematically into two different kinds. One is chaotic. These clumps occur fairly regularly but not completely regularly. That's a sign of chaos. And you can sort of say how much of this is due to chaos. And then what's left over, you say, I have no idea what that's being caused by. We'll call that random. So you get this idea that the variability in the spacing has two components, a chaotic one and a random one. And that's where the FracMat machine and the chaos theory comes in. The machine's in the background here. The big thing in the front is just feeding wire. And it's coiled on the metal rod. Then the test coil is taken off and placed on a stage at the top. And then a laser micrometer runs along and automatically measures all of the spacings of all of those coils and feeds all of that to a computer. Now, if you just looked at the spacings, how wide is the gap compared to which coil are we looking at, you get an irregular curve like this. And the computer can display that just so you can look. And actually, that's clearly bad wire. But now what the computer does, the question is, how bad? Can we assign some numbers to say exactly how bad it is? So the computer does some chaos theory magic on it and turns it into, all those numbers get turned into this sort of blob. And there are two important things about the blob. Is it a big one or a small one? The bigger the blob, the more randomness there is. And is it a long, thin one or a short, fat one? The shape tells you how much chaos there is. Having got those two numbers from looking at this blob, you plot them on a classification diagram. The random component one way, the chaotic component the other. And here's our sample. And if we look more closely at that, it's in a region that's labelled very poor. So we know that that particular sample of wire is extremely poor wire. So that's how chaos can help improve technology. Chaos really does give us useful and interesting insights into the world around us. Now, one of the big themes of these lectures has been that what's interesting is not just the things that go on down on the ground here on Earth, but also the grand cosmic questions up in the sky. Life, the universe, and everything. And one of the really interesting applications of chaos is to the planets. It turns out that the whole solar system is chaotic. Now, 4 billion years ago, when the Earth formed, it was hot, it was a molten ball, it cooled, life grew, and it's been around ever since. So we all feel pretty safe down here. So did the dinosaurs 65 million years ago, when a very large meteorite, so most scientists now believe, came crashing through the atmosphere and wiped them all out. And impacts like that have happened a lot closer to the present day. Comet Shoemaker-Levy 9, not long ago, split into about 20 fragments and crashed into the planet Jupiter. Here is an explosion just round the back of Jupiter caused by that comet. It's bigger than the Earth. Now, they couldn't see the actual impact because it was round the back, but when the Hubble telescope got pointed in the right direction to see what was happening around the front, they saw the aftermath of the explosion. They saw a big scar in Jupiter's atmosphere. And a little bit later on, there were several fragments and they saw a whole pile of scars in the atmosphere. Enormous. It's as if Jupiter had been subject to something far, far worse than a nuclear war. Thousands of nuclear wars all going on one after the other. Enormous explosions, just caused by that comet. So what is it that actually sets up the conditions for that kind of impact? It's chaos. It's the natural behaviour of the solar system. At any time, a big rock could be moved out of its orbit and flung towards the Earth by the workings of the law of gravity that Isaac Newton discovered. And it doesn't have to be some intruder from outside, from the depths of space. It's simply one of a large number of rocks that currently go harmlessly around the Sun in between Mars and Jupiter. These are the asteroids. Let's see how that happens. The Earth, nice, blue, comfortable planet, third from the Sun. Beyond it, Mars, big gap, and then Jupiter. But in the gap are the asteroids. Lots and lots of rocks of different sizes. They're clumpy. There are gaps. They're called Kirkwood gaps after Daniel Kirkwood, who first discovered why they happen. They're caused by Jupiter. When an asteroid goes round so that it's synchronized in some way with Jupiter, Jupiter pulls it out of position. The biggest gap is where the asteroids go round 3 times as fast as Jupiter. So every third time they come round, Jupiter gives them the same pull in the same direction, cleans them out. There aren't many asteroids in there. And when they come out, they can get flung in various directions, and one of the things that can happen, they cross the orbit of Mars, and Mars can send them heading towards that nice, comfortable blue planet down there. And here is the big rock coming in, and down below, the dinosaurs are waiting. Now, if one of those is coming towards us at the moment, we will probably see it coming. And we know there aren't any right at this point. So I wouldn't worry too much. You don't have to leave the lecture yet. However, if one of them was coming towards us, there's not much we can do about it except say, oh, look, there's an asteroid coming towards us. So it really is important to understand chaos and learn exactly how it works for that reason and many others. Chaos is not just randomness. It's randomness with hidden patterns. Now our job is to draw out those hidden patterns. And it turns out that the most important hidden patterns are geometrical. They're shapes, but they're unusual shapes. Let's go back to Jupiter. One of the best known features of Jupiter is the Great Red Spot. It's been there for hundreds of years. It's a big storm, a vast hurricane on Jupiter. And when the Voyager spacecraft got a look at that, it noticed you get complicated, turbulent vortices spinning off. What we see on Jupiter is turbulence, big vortices, smaller vortices, very small vortices, and if we could look closely, smaller and smaller and smaller ones. That's an example of chaos, but it's chaotic geometry. Any geometrical object with that structure is called a fractal. So fractals are the geometry of chaos. They're unlike all the usual things you get in geometry. You take something like a circle. If I've got a circle and I make it bigger and bigger and bigger, look more closely at it, it just gets flatter and flatter and flatter. Nothing interesting there. If I start with a sphere and make it bigger and bigger, it just seems flatter and flatter like a plane. This is why a lot of people thought the Earth was flat in ancient times. Fractals are different. When you magnify them, you see more and more and more structure. And yet, that very intricate geometry can be created by very simple mathematical rules. And the next demonstration is going to show us an example of a fractal pattern created by simple mathematical rules. Okay, now I need some assistance for doing this as well. Young man there. Okay, and your name is?
Richard.
Okay, Richard. Now, what we've got here for you, that's it, you might as well stand there, is a whole pile of stuff. There's a triangle marked 1, 2, 3, a pile of red dots, a three-sided die. It looks like an ordinary die, but it's got a 1 on that side, and it's also got a 1 on the opposite side. And the same for the 2 and the 3. So you hold that for a minute. Whatever you throw with that is either a 1, a 2, or a 3. And you've also got a ruler. So what we do is we start by putting a dot somewhere in the triangle. I'll put it in the middle. Now roll that. It's a 2. I want you to find the point halfway between that dot and corner 2. I'll pop it in there if you tell me where to put it. That's it. Let's have a measure. Okay, what's that?
11.
Okay, so about there. And now do it again. 3. Okay, that's over there. So halfway between your new dot and 3. About there? Okay. And that's right, we can put that one back. And once more. 1. Halfway between your new dot and 1. Right, and that would be?
16.
Okay, that's great. Okay, thank you very much. So there's some simple mathematical rules. Roll the die, start from wherever you are and go halfway towards the corner that the die has given you and just repeat. The question is, what shape would you expect to see? Well, the most likely thing you'd expect to see is just a sort of smeary mess in the middle of the triangle. But let me show you what happens if you do it thousands and thousands of times. Again, we'll use the computer and we'll see exactly what pattern builds up. Okay, we start with random looking dots, nothing very interesting, just sitting in the triangle. But now we'll just speed it up a little bit, keep going, and you'll start to see very, very beautiful, surprising mathematical pattern appearing here. This is called the Sierpinski gasket. Gasket, all of you car mechanics will know, a gasket is the thing you take out of your car and it's full of holes of different sizes. Sierpinski, Wacław Sierpinski was a Polish mathematician who invented this shape for totally different reasons. It's got big holes in the middle, and then in the pieces around there, smaller holes and smaller holes and smaller holes and smaller holes, and mathematically those holes go on forever. And that's typical of fractals. Simple rules create structure on all scales, even the finest. Let's look at a few more fractals. Fractals were invented by a man called Benoit Mandelbrot, and this is the Mandelbrot set. It's created by a simple mathematical rule. It has lots of structure. We're zooming in on this, looking closer and closer, and in the middle of it, coming out, that blob that looks a bit like a cat on one side, that's a baby Mandelbrot set. It's got all the structure of the original. So if we zoomed into that, we'd just keep on getting more and more fine detail. It would go on forever. Lots of different fractals have been invented by mathematicians. I'll show you a few more of them. They're choose your formula, do what you like, mess around. We will see some more fractals. This one, we've animated a whole series of them together. It looks amazingly complicated, but it's created by a very simple mathematical rule. You just can't believe that something as nice as that, intricate as that, could possibly come from one rule. Here's a different kind of fractal called a Julia set. And again, a very simple rule gives rise to extremely complicated structure. Okay, now that's a clue not just to mathematical shapes, but to shapes in nature. Lots of shapes in nature have the same kind of intricate structure on lots of scales. And the message from the mathematics is there are probably simple rules behind that. Now, a very familiar object which has structure on a lot of scales is this. Cauliflower. We're going to look at the mathematics of cauliflowers. Now, to a mathematician, what can you say about a cauliflower? It's sort of lumpy. And the lumps it's made of are sort of lumpy as well. And the lumps they're made of are pretty lumpy too. So it's kind of lumpy on all sorts of scales. Now, I want someone from the audience to help us really pull this cauliflower to bits. Okay, young man here. What's your name?
Yura.
Sorry?
Yura.
Yura. Okay. Now, come here. You've got the knife. I've got the cauliflower. Careful with it, so it's fairly blunt. And what I want you to do is cut me out a really nice big chunk, big as we can get. Here we go. I'll just make a bit of room here. Of that cauliflower. Get in there and cut out a big chunk. If it's not big enough, we'll cut another one. Okay. Cut right through. Here we go. Let's see what we've got. That's pretty good. Let's have that out. There we go. We've got quite a nice big chunk there of our cauliflower. So, 2 generations, first generation, smaller one. This is a miniature cauliflower. It's almost as complicated as the original. In fact, it looks much the same as the original if you blow it up. Okay, now let's go for another one. Can you cut me off that bit? That's the stuff. Probably catch it here. 3rd generation cauliflower. Take one of the lumps, take a lump off that. And I'm sure you can cut me yet another one off there. So we've got now 4 generations of cauliflower. And I think we can go a little bit further still. Go on. Okay. You got it. Okay. So now unto the 5th generation of cauliflowers. Okay, thanks a lot. That's great. So what we hope is that we could produce something rather like a cauliflower from simple fractal mathematical rules. This is a home video of me on my holidays in the mountains, looking at the view. Isn't it amazing? Well, of course, you're all realising there's something a bit suspicious about those mountains. They are, in fact, over here. There we go. I can pick one up. It's just a rock. It's an ordinary rock. Put it back. So, you may not think that's very impressive, but it actually works better than you'd expect for a few lumps of ordinary rock. Those are reasonably convincing rocky backgrounds. They look much bigger than they are. This is because mountains are fractal. Little bits of mountains, rocks, look convincingly like big bits of mountains, the whole mountain. And it's possible to use the fractal rules like that to generate fake mountains. And here we have the first time anyone ever tried doing this. This is a completely artificial fractal landscape. There are much better ones now, but this was the first they ever did. They're not putting the complication in that sort of detail. All they're doing is putting in fractal rules for mountains and seeing what shape you get. Cauliflowers, mountains. What else around is fractal? Well, ferns are fractal. Ferns are extremely fractal. Ferns are about as fractal as you ever get. Look at this frond of the fern. Sticking out from the side of it are little miniature fronds, and they just look like ferns again. Sticking out of the side of those are little miniature ones, and they look like ferns. And sticking out from the side of those, well, eventually it stops looking like ferns, but it goes on for quite a long time. So that means it ought to be able to generate ferns mathematically in a very simple way from fractal rules. And a mathematician called Michael Barnsley worked out how to do this. This is Barnsley's fern. generated by mathematics. It consists of lots of copies of itself. We've shrunken a bit, turned it sideways, stuffed it in, and there it is, one of its fronds. Do it again. Shrink, turn sideways, move it in, join it on again, and you can just go on doing that down and down forever and ever. So mathematical rules can generate nice pictures of ferns. So what, we're all thinking, what's the point of that? Well, the point of that, as Barnsley realised, is that's actually very important. That is the basis of a multi-million-dollar industry. Barnsley now runs a company that makes large amounts of money by exploiting the idea behind that. And the idea behind that is not ferns, it's image compression. We have to send lots and lots of images nowadays all over the place. You send them from fax machines down the telephone lines. You transmit them from satellites down to television sets. Or you store them in computers and put them on the screen. Now, the problem with pictures is they take up an awful lot of space in your computer or time on your phone line. And it's rather like this. Imagine this phone book contains all the information you need to store one picture. Okay? Rather a lot of information in a phone book, but to get a really good picture, high quality graphic, you need a big amount of information. It would be so much nicer if you could take just some small part of that information and somehow store the whole picture in this much smaller space. And that's what Barnsley realised that fern was doing. The fern is very complicated, but the fractal rules for making it are very, very simple. They're like our fractal game there that gave the Sierpinski gasket. The gasket's very complicated, but the rules are simple, and given the rules, you know how to put the gasket together. Given the rules for a fern, you can build the fern. And what Barnsley realised is every image is like that. They're not just like the ferns, they're not artificial looking things. For example, if I look round this room, I see lots of small faces up at the back and lots of big faces down at the front. And while they're not the same faces, they're very similar to each other. So I have a little fractal rule that says your face up there matches your face down there if we stretch it a bit. Or we can look at the magical maze. It's been sitting behind us the whole lecture. This piece of the magical maze looks very similar to this piece. They've both got a dark patch, a lighter patch, and a green bit. So if I can patch together enough bits and pieces of the picture and say this piece looks like this piece if you squash it and move it, I can throw away the picture and just keep that list of rules. And if I'm clever, I can make that list much smaller than the amount of information needed for the picture. Now let's see how that's really done. Henri Poincaré, one of the founders of chaos theory 100 years ago, though he didn't know that's what he was doing when he did it. We're going to compress Poincaré. First we'll zoom in on some part of the picture. Poincaré's nose. His nose is made up of lots of little tiny squares, black ones and white ones. And we can break them up into, say, 2 by 2 squares and look at the different patterns you get. There are only 4 types of pattern appearing in Poincaré's nose. Don't worry about the black ones, let's look at the ones that got white in. Here are the 4 patterns you see. Now we look at his nose on a slightly larger scale, look at slightly bigger squares. That one is the same shape, twice as big, as the first of our little squares on the right. That one is the same shape, twice as big as the second square. That one's the same shape, twice as big as the third, and this one is the same shape, twice as big and moved around as the fourth. So if we listed all those rules, we could reconstruct Poincaré's nose. But we want the whole thing. So we have to look all over the picture, all different bits and pieces, until we find enough patches to put it all together, and then from just the rules for how those patches relate to each other, we can reconstruct the picture. Now let me show you how we reconstruct it. It's like the way we drew the Sierpinski gasket. The first attempt is a bit fuzzy, not very good. Run through a second time refining it, it gets much better. Once more, you end up with a picture that is, to all intents and purposes, as good quality and with all the detail of the original picture. but it occupies perhaps 1/100th of the amount of space in the computer's memory. So that's extremely important. That means instead of one TV channel from a satellite, you could have 10 channels coming from the same satellite. So this kind of thing happens all over the place. The Encarta CD-ROM, lots of you with the computer, it's a kind of encyclopedia. It's on one CD-ROM, it's got 8,000 colour pictures in it. And yet they're there. They're all compressed. They are compressed by Michael Barnsley's fractal method. So when you look at pictures from a CD-ROM, most of the time they're compressed, and they may well be compressed by the fractal method that I've just shown you. So what have we learned? Isaac Newton taught us that the universe runs on mathematical rules. But at first sight, that means everything is determined, everything is predictable. If you know where you start, you just run the rules, and you can tell exactly where it goes. Chaos tells us it's not like that. The slightest error in measuring what it's doing now means that when you propagate those rules into the future, you get lots of different possibilities, and you don't know for sure which one's going to happen. So that's how it's possible for things to be unpredictable in a clockwork universe. In fact, were it not for chaos, this would be a very boring universe to live in, because it would be following mathematical rules and generating rigid mathematical patterns and never doing anything unpredictable. Who wants to live in a universe like that? Now, it turns out that fractals are everywhere, literally. Saturn's rings are clumpy. They are, in fact, fractals. The whole solar system is clumpy. Matter is concentrated in the planets. Stars clump together into galaxies. Galaxies clump together into galactic superclusters. The entire universe is like a fractal foam, with the matter where the soap is, and huge voids inside all the bubbles. Not only that, we're all fractal. The system of veins and arteries, branches and branches and branches, getting smaller and smaller and smaller. It's a fractal. Your nerves are fractal. The thoughts that go across your mind are fractal structures in your brain. So we're not machines living in a clockwork universe. We are fractal beings living in a chaotic universe. Now, something else about the universe that's important. The laws of physics are symmetrical. And that's what I'm going to be talking about in the final lecture.
If you'd like a booklet or a video pack of all 5 lectures, which includes a booklet, please send a cheque made payable to BBC Worldwide Limited, to BBC Worldwide, PO Box 5620, Newbury, RG 14 2YA. The booklet costs £3.99 and the video pack is £29.